Morning, everybody. Morning. So this is offensive retooling in .NET for red teams. My name is Dimitry Snezhkov, and security consultant for X-Force Red, IBM Corporation. Shout out to X-Force Red team. Current focus is on offensive security assurance testing. I think I need to move this up a little bit. Tools, code, and I like to do the operator stuff, or at least try to do a little bit more of that. And I'm from Chicago, but I was born in Ukraine, and there is no "the" in Ukraine, just so you know. Okay, so let's talk offensive things, right? Things that basically make other things go under the detection radar on Windows. We're going to look at it from the offensive operator, red team operator perspective, and let's look at the system and some of the pain points that we have as a red team operator to overcome defenses, right? So we'll talk about some ideas. We'll build things, right, or at least attempt to build things with code blocks, and we're going to do this on live system. And so the idea is that we're going to have a couple of concepts. One is code is data, data is code. We're going to go over that. And also the other concept is slim cradles and dynamic payloads. So if you think about how the offensive recon happens while you're on the machine, the issue for the red team operator is the first mover advantage, right? You have to move first. You drop down the machine, you're in the operating system, and you have to start discovering that. So the first move kills you, okay? So the better you can actually prepare to, or at least discover some of the things in your surroundings, the better it is for you. And so the first stages of recon on the operating system is very important because you have to move first and you have to collect the information. And the issues that you face are multitude, right? You've got logging on shells, you've got hooked instrumented binaries, sometimes you have sandbox execution, and sometimes you have quiet systems that when you move, you reveal yourself, right? And so the idea here is that known static offensive tools that you bring into the environment to do your recon or discovery get flagged because they're known, right? You've got the network effect because they've been used everywhere. So the idea is that why don't we approach it from the perspective of retooling, right? When we drop on the machine, can we retool? Can we create custom stuff? Can we create building blocks right on the live system? And so sometimes those blocks may be better than static tools, right? We can still utilize some of the things, some of the facilities of the operating system to do our coding there. But the problem becomes that, it's just that, it's live, right? Live retooling, when you code live on a system, it has a bunch of advantages as we discussed. It's minimized fingerprinting, right? But it has disadvantages. First thing is dev time is very high, right? You're doing it on live system, you have bugs, you will be able to reveal yourself right there. So your operational security is minimized. And so you also have to get to the point where you can actually code well on the system without being discovered. So the idea here is, for our strategic purpose, is that we need to be able to recon under the radar for a long time and not be loud enough to get discovered. We also need to be able to quickly retool for things that we discover on the system, things that are unknown. And essentially, we want to deliver something into the environment that we can operate on as far as tools and other building blocks. So from the tactical perspective, what do we want? Well, at least we want support and transfer of payloads right into executing cradles, right? So we have a small cradle, we're going to talk about this, and then we're going to drop some payloads in it. We want to build those payloads and execute them real time, and we also want to support evasion. When we go and start thinking about properties of things that we want, we also want to minimize artifacts, right? We want to the best possible way, minimize some things that might potentially be used for forensics later. We want to have reasonable interface with legacy tools or operating system because we cannot do everything on our own. We have to drop down to possibly low level. And we have to have improved operational security from the get-go. Okay, so this idea of a slim payload delivery cradle where you have a very small footprint of a cradle that still allows you to enhance your capability iteratively, right? So you start treating code that you bring in as data, and you treat data as code, okay? We're going to see how that works. And then along those lines, we're going to look at decoupling compilation of your building blocks with execution. So when defense looks at it, they see either or, compilation or execution, but they can't actually make the two together. Okay, so what are the current mechanisms for retooling? We've got PowerShell, great. We've got WMI. We also have unmanaged code and also managed code on the machine. All of them have pros and cons, right? It's sort of like pick your poison. And so for our discussion, we're going to actually work at the .NET. So there are different pros and cons for every method here. But our biggest concern here, if we're working in the PowerShell, we need to remove the logging, right? Right now, everything is logged. We also need to maximize the ease of use for our tools. So .NET is an interesting sort of layer that we want to concentrate on. It has tons of advantages. It has been around for a while. It has a lot of APIs, right? It has great utilization properties, meaning you have network API, you have operating system access API, and .NET is actually not logged, right? Whereas PowerShell is, .NET is not. But there are disadvantages. Slower development time. It is a statically typed environment, right? We have to be able to develop really fast. There is no REPL in it, right? You can't really evaluate your expressions right off the bat, or at least you need to be able to build the environment so you can actually do this. And compilation is a big issue, as we will see. Okay, so how do we solve that, right? We need to keep our advantages, but we also need to remove all the disadvantages from it. So let's try to, can we even build that out? So let's iteratively try to build this managed execution toolkit, right, that will allow us to do so. Going back to .NET, what is .NET, right? .NET is API, a wealth of APIs. It's common language runtime that actually runs your code. And it's also compilers, right? Compilers on the box. Now, there are cousins to that first-degree relatives, right? There is a code DOM, which we'll talk shortly about, and there's also a DLR that we're going to talk as well. It's really easy, right? Conceptually, source code, compiler, executable. The problem becomes is that, well, how do you compile in .NET? Well, it turns out that csc.exe or msbuild, well, to the lesser degree msbuild, csc.exe is pretty much always guaranteed to be available because .NET itself actually relies on it. For example, XML processing, compilation, and whatnot. So CSC is available. Let's look at the code DOM. Code DOM is the code document object model. Just like in, say, HTML, right, in the browser, you have some model that your code is or adheres to, right? Some tree that you're building. In .NET, it is code DOM. Code DOM basically means that, okay, your source code, when it compiles, it has this AST tree, and then you can do whatever you want with it. You can compile it to intermediate language. You can compile it to, you can merge other source code in it and compile it. And so, for example, ASP.NET, XML Web Services, code wizards in Visual Studio all use code DOM. Okay, so source code on top of source code with code DOM API compilation into either more source code or end result is the executable. So we're talking about code emitting mechanisms here, okay? So why not apply code DOM to building our first REPL here, okay? So we need to be able to dynamically compile C# or VB or JavaScript, whatever, or JScript rather, whatever you're mostly comfortable with. And we're going to use that REPL to evade the actual discovery of a payload that we're bringing in. We're just going to paste our code into REPL and execute it. Okay? So the way we're going to do this, we're going to use the API for compiling your code right from the .NET Cradle. Okay? Your Cradle is very small, but it has .NET, right? So .NET always have C# code provider. And so we can actually introduce various options into compilation right into the code. There are some evasion mechanisms that can actually happen for defense guys out here. .NET doesn't necessarily need to compile to DLL. It can compile into temp, so that if you're watching for DLL, it's not going to happen. And so let's look at this feature of this managed execution code called Seesaw, right? Our goals will be to dynamically compile the code, do the REPL, and then try to load assemblies in memory, try to increase our utilization while decreasing the footprint. Okay, so how do we do this? We do this with contracts. So what is dynamic compilation? Well, it's just a string of code. It's your code, it's my code, it's somebody else's code. So why not we pre-tool some of that pipeline and say, okay, well, 2 out of 3 of the string of the code, right, is going to be ours, and then 1/3 is going to be yours, whatever you're going to paste in REPL. Okay, so we're going to mix and match something that we pre-tooled to what you are going to paste in REPL. Okay, so half of it is going to be user submitted, half of it is going to be tool generated. Again, evasion because you're pasting half of the code of the generating binary. Okay, so defense is not going to see the full picture here. So we're dynamically compiling. We're creating, so we talked about a contract, right? So in order for us to do REPL, we should be able to get some results out of things that we compile. So our code adheres to just 2 API, 2 functions, get results and dispose. Dispose is there so we don't leak memory and we can actually iteratively do REPL. And so what you get is a REPL that you paste your directives using system, IO, whatever the case may be that you're trying to invoke, and then the actual code that you're executing. In this example, you're just listing providers on the system. All of that is interactive, right? And so what you come out with is that you've preserved the scriptability of your dynamic languages, sort of, right? And you also evaded some of the defenses for the code that you execute. But there are disadvantages in it. It's sequential, there is no abstraction, there is no reusability, and it's really, really quick and dirty. Okay, so we should be able to do better. Okay, so let's build CSX extensions. CSS extensions build on the previous contract, but they improve on it. So to give you an example is that now instead of having get results and dispose, we're going to do pre-launch, run code, and post-launch. So you can actually create hooks into what you do when you're running the code. And to illustrate this, for example, you want to invoke a functionality, right? You create a sliver of code, your C# code that is going to be dynamically evaluated. And you just need to define run code, which is going to get text out of the clipboard. And then you do disposition. So this is your meat of the code that gets involved by the REPL itself. Not REPL, but the Seesaw itself. And then in this case, I left my pre-launch and post-launch functions empty because I do not want to do any additional processing. And so this is text, right? Code is data, data is code. And so this text gets executed within the cradle. So you're not bringing in DLLs or executables in the environment. You bring text, okay? And once you bring text, you should be able to compile it. So for example, Typhoon is the managed prototype that we have, and Seesaw is just the part that deals with C#. And so, as you can see here, we're pasting clipboard manager.cs. It's our sliver of code into it. So we compile it, okay, and then we run it. And so we get the results of our clipboard. And for example, if we want to copy master, we do exactly the same. We get master from it. So we decouple compilation from execution from the fact that we're not actually bringing in any DLL or executable, we're doing it live on the system here. But there lies a problem, okay? And the problem is that we're dropping some temporary DLL on the box, which is not going to be malicious because it's going to be just part of the code that we're executing, right? But it's still a DLL, okay? And so we're not invoking csc.exe, so for defense that are watching for csc.exe invocation, we're not playing in that, right? We're not directly going to command line and invoking csc.exe. Therefore, you will never see this in your logs. However, csc.exe is actually still invoked on the back end, okay? Through code DOM, it's still done. So that's really bad for us as red team operators because we're leaving artifacts in. The okay part is the presence of the temp files. We're going to solve that later. The okay part is that we cannot delete the DLL while we're using it because of the way Windows works, the way .NET actually logs the file, and you can't really delete it. Naming of temp files is not also under your control, which is also okay-ish. And you can't unload the DLL once you load it up. Okay, those are the real issues that we need to contend with. Okay, so and so when we do compilation.NET, we have an option to generate in memory. A bunch of people actually take it as, okay, well, we'll generate in the memory, and then we're going to forego all the DLLs on the box. We're not going to drop any artifacts. This is a misnomer, right? You still generate. Memory means, for .NET, for some reason, it means in temp folder, right? So you still have artifacts. Here's your source code that you're dropping for your defense. Here is the temporary files that you're also dropping there. And so don't be fooled by generate in memory, right? So we have to be able to solve that. And also, if we look at the process monitor, you see all these intermediary smaller DLLs that are being compiled in when you do csc.exe. You've got your code, you've got pretty large footprint, even though you're not invoking CSC directly. Okay. How do we remove artifacts? Well, we want to delete our loaded assemblies. If, for example, we're on a long-running gig and we've created our payload and it's a CSC or C2C agent that needs to be long-living and needs to connect out, it runs in memory for hours, maybe days, maybe weeks, and yet all the DLLs that we're sourcing, albeit temporary DLLs, they're still present on the box. So defense has a big chance of discovering us. We need to be able to delete them. We need to be able to unload them. For example, we've loaded some functionality, we're done with it, we want to unload it. Also not possible, we want to do that. And then, as you saw, there are a bunch of artifacts like temp directories, CMD files, CSC files, or whatever the case may be. However, the problem is that none of that is achievable by .NET, at least in classic .NET, directly. How do we deal with this? Well, for example, in this code, you can't delete a file. So, for example, you've compiled an assembly through our methods, right? We brought in the code, we've compiled it, we ran it, and perhaps it runs for hours, but we can't delete the assembly that we've just loaded. Okay, it's locked. Well, it turns out that we can use application domains, right? Like, for you to code this block, you just need to introduce that into a different application domain. And then application domain has a separate channel for loading your DLLs. And once you're done with it, you just remove the entire application domain, which unloads all of your DLLs, and then you can deal with that. That's also an invasion, right? So if you're watching for things, if you're trying to program it that way, you're using it. If you're a defense, then you're watching for it. Okay, we kind of start solving these issues. The other issue that we have as an operator, how do we use operating system facilities? How do we use interrupt? Well, what is interrupt? You have investment in your unmanaged code. You've got your COM, you've got your ActiveX, you've got your C++ programs that you have on the box that you may potentially want to use, so you don't have to create them from scratch, right? And so for .NET, it's a little bit hard to do because it's managed code. So interrupt in .NET is achieved by a process invoke, or platform invoke rather. Right? It's a system runtime interrupt services that says, okay, well, how do we map a LP void pointer to, I don't know, maybe an int in the .NET, right? And so the interrupt basically says, okay, well, that's how you do it, and that's how you invoke your operating system facilities from .NET, okay? So also evasion, right? Because we're not strictly working at .NET anymore, we're actually reaching out for COM, for ActiveX, and whatnot. And so from defense perspective, you should be able to trace that path, right? From the offensive perspective, we want that. How do we do this in code? Well, the way to use interrupt services is that we are creating a attribute, right, for, let's say we want to load user32.dll, we want to find window X function, and we want to invoke something in it. Unfortunately, this is a compile time lock, right? You need to be able to resolve attributes like DLL import and files, or rather functions that you find at the compile time. You can do this, but, and you can actually use that in a different code. So you can actually compile DLL with your just the prototype or a stub that loads the DLL import, and then you use that little DLL in a third-party code. And so the way it looks in the in code is like this, right? You for example, for clipboard manager that we've been using, you bring in user32.dll, a bunch of other dependencies, and you execute your code by using all those linking. But like I was saying, it's a compile dependency, so you actually need to know upfront what DLL you're loading, okay, and what function you're looking for, and how you're invoking this. It's bad. Bad because we're aiming and striving for dynamic retool. And so if we start being more dynamic, we should be able to be agnostic from what DLL we're actually loading at runtime. For example, I may have some logic in my code that says, okay, on the system I discovered Oracle, right? I want to be able to dynamically load Oracle DLL into my code and work with it. Currently, I don't have a way to do this because I have to be able to know the interface for it and the functions that I use. So let's do a better dynamic interrupt, right? So there is this code at Google, right, the sliver of code that I stole that allows you to do dynamic DLL imports. Essentially, all you have to do is point to existing DLL on the box, and if you know what functions exist in it, you can actually dynamically load it at runtime. .NET 4.0 supports dynamic keywords, right? And so those dynamic keywords allow you to do so. Bunch of reflection, bunch of emission API that you're dealing with here, but that's good for offense because you're evading, right? No tools walk directly to the bottom of the dynamic, well, at least not that I've seen. Okay, so now we can use this concept and actually bring it back into REPL. Right, and so we can actually say, okay, well, REPL, why don't we go into our little REPL and say dynamic user32, and from that dynamic user32, I'm going to get a message box. If you think about what just happened, you're actually creating a full scriptable .NET interrupt bridge, okay, for things that you want to do on the system. No more knowing well, you still obviously can bring your own code, but it gets a little bit more dynamic here. Okay, so we mostly met our seesaw goals, right? We're dynamically compiling C# code, we're doing REPL, we're loading assemblies, we're unloading assemblies, we're deleting files, we're taking care of some of the interrupt things. Okay, well, if you saw in the Process Explorer, we're still leaving a lot of artifacts. It is not good for us and we want to do better. Well, can we achieve a better scriptability? Can we actually forego app domains altogether? Because they're a pain to work with, right? And it has a lot of code that you need to supervise, right? It's very much assisted execution. Crazy idea, right? Why don't we not compile anything? Well, you ask, how do you actually execute code if you don't compile anything in an environment that actually forces you to compile something into some intermediate language? Okay, well, let's review that. Okay, so we're bringing a different set of code or APIs and call it Delirium, right? What that means is we're banking on dynamic linking runtime. So we worked with CLR before, now we're working with DLR. So what is DLR? Okay, DLR is a .NET set. It's a set of APIs in .NET that allows developers to create dynamic languages on top of .NET. Plain and simple. When Java wanted the whole world, .NET said, okay, well, why don't we woo developers over to us, and how do we do this? Well, we need to create an interop way of creating, let's say, porting, I don't know, Java, Python, Ruby, whatever the case may be, right on the .NET. How do we do this? Dynamic linking runtime. Okay, so it sits in between the common linking, common language runtime that you're executing in static types .NET, and then the actual language that you're trying to create. So essentially what we're doing, we're creating a dynamic language on top of .NET. We want to move away from, in plain terms, we want to move away from strongly typed language that we have to supervise and be assisted to something that is very simple, right? That we're doing in Python, right? We're doing script object.count plus equals 1, done. Okay? So it brings a lot of advantages. It brings some disadvantages. Let's review. So first of all, you need to, there are two namespaces that source in DLR and .NET. It's Microsoft.scripting and Microsoft.dynamic. This is the sort of the middle layer that allows you to create languages. And then you create languages. And so it so happens that a lot of languages have been already created. For example, IronPython. And so IronPython is nothing more than just an overlay of Python language on top of the DLR. We move away from strongly typed dynamic types, which means speed of development on systems. Python is much faster to develop than C#, okay, for many reasons. And so we hide complexity. On top of it, we escape a lot of things that defense is doing to prototype us. Here's the difference, right? You've got the C# static types. What that code does, it's basically, it goes out to google.com and fetches a page, but it does it in the C#. Counter shell in the PowerShell is a dynamic way of doing so. But we know we want to contain, we want to assume the dynamic nature of PowerShell, but without PowerShell, so we do not get logged and flagged. And so you can see the difference between how easy it is to do in PowerShell. Well, in a C Python, you would import your URL library, you would go to Google directly, you would print content. It's comparable to PowerShell, it's very easy, it's very dynamic. And so is in DLR, right? All you do is you bring exactly the same web client as you would in C# or PowerShell, and you go to that google.com and you bring that page. So if you think about that, what just happened here, we just started coding in Python, which is 10 times faster to develop in for many people, right? And we also maintain the flexibility of the PowerShell, and yet we're actually directly interfacing with .NET. Okay? This is what DLR gets you. Okay? No compilation, no artifacts on the system. No temporary files, no code, nothing. So for defense, if the offense moves into DLR and start creating code in IronPython, for example, properly instrumented, you lose absolutely visibility into what they're doing, which is good for us. Defense needs to look at that further. Okay, so let's look at the example here. What are we doing? If this was our REPL and we were actually using the web client through interactive means, if this was our C# code that we were actually sourcing for compilation, then DLR is just you import the CLR, you add reference to system, then you import system, and then you execute Python code. And so we can start doing compilation. If we did that in C# before, we can do compilation of your C# code right from the Python. Okay, so you get into even more stealth this way. And we're actually going to see how we do this here. If I can find it. Okay, this is a little bit more, okay, here it is. Okay, so what just happened here? If you look at DLR example, we're using interrupt to pop a box, or pop a message box. Well, we'll pop a box too. But message box, right? But the way we're bringing bring the attribute in is no longer we compile the C#. We're actually doing a Python string that is also dynamic. We can bring it from outside or type it out. And then we're actually doing compilation of our code in Python. And then we're bringing user32 from within our Python. Then we do some setup for pointers or whatnot, and then we're calling it dynamically on the message box. And so on this command right here, first you bring in Python, right? Iron Python code, not executable, into the cradle. It itself compiles itself with dynamic interrupt, and then calls a system function on the interrupt. And so you get this, all right? You're getting way out of the defense introspection path completely, right? And if you look at how those dynamic binaries are constructed, they're very much emit dynamic and a lot of reflection in there. And so there's going to take an analyst to actually go in and see, well, what is this Python code is doing actually? Actually, it's not even Python code, it's your MSIL code, right? Like intermediate language. Okay, so our goals. Again, leverage DLR, we saw that. Then we can compile Python to exe without bringing any Python runtime except for a small DLL for Iron Python, which sits on top of the Microsoft Dynamic Language. And so you get a lot of sort of good things with Python, right? You get standard library sometimes. You can actually bring it in. And so you can even code without dropping directly into .NET construct. You can actually work with Python code itself, like Python-based coding, right? There are certain evasions that you can do because Python, for example, to bring in standard library, doesn't need a DLL, right? It just needs, well, it needs a zip file with a standard library. You can disguise it as .x, right, which is also a zip. So there are a lot of time, a lot of things that you can do with it and move forward with your evasion. So easy, right? It's DLR is just .NET technique. You can call WinForms, you can call operating system facilities, you can call threading, you can call whatever you want on it. You can even compile your Python code into assembly DLL that you load from your C# or any other language. And so you're moving into the space of handing off generated libraries and assemblies to a third-party process, potentially on a different machine. Compilation happens here, invocation happens in a different way. You can serialize things, you can call them in a different way here. You can even compile Python REPL itself in Python and generate a x64 executable on the machine. So you don't need to bring in your Python 2.7, 3.6 for Windows and have this huge distribution there. You can actually compile it. Okay, you can work with C types if you want to, but the problem with the problem that we're facing is how do we actually bring that Iron Python DLL in the first place, right? But that's also a challenge. You could potentially, well, first of all, we're bringing code as payload, right? That's clear here. We're bringing Python code, nothing else. But we need just one dependency. We need that Iron Python.dll. We somehow need to bring it into the environment. We can bring it in as part of the typhoon.exe as an embedded resource, We can bring it in app-config instruction as a fetch. And we can actually do other crazy things like net modules. And let's look at those. Okay, so the first is we can bring the ironPython.dll as an embedded DLL dependency. What that means is that you are statically compile a DLL as a resource into Typhoon, and then you are hooking your assembly resolution for when it tries to find ironPython.dll into itself and say, well, go look in my resources. Okay, don't look on the file system, don't look on the network, go look in my resources. So I load ironPython.dll from my resources within the executable, which is really powerful, right? Because if defense is looking for a specific ironPython.dll, they will not find it, because it's going to be inside of typhoon.exe, and as long as you don't have whitelisting for typhoon.exe, then you should be good. Other ways, other building block ideas, because we're basically doing ideas like how do we compile, how do we move away from detection here. You can actually use CSC itself to compile your Typhoon right on the system, if you choose to do so, and then you can link it to ironPython.dll, and you can actually do you can actually bring code as net modules. So let's see what net modules are. Okay, in .NET assembly linking, there is this thing called net module. A net module is an incomplete assembly that is not loadable and is not invocable. It's a sliver of code, well, it's a half a binary DLL without a metadata, right? So you can have just a blob of data sitting on the box, and unless you add metadata to it that says, okay, well, that's an assembly, no one's going to know what it is, right? It's not even, you can't decompile it. So net module is just that. Like, for example, you can compile different pieces of code into their own net modules, drop them on the box. They will not get flagged by anything because it's not executable code. And then you basically link them through metadata. Okay? And the way we can do this, let's take a look at it here. Okay, so again, we're operating within ironPython here. So for example, we want to do screen capture. And let's say this is our first module. We're bringing user 32 as we did before. This is our second module, which is GGI 32 that does the actual capture. Then what we do, we generate net module and put it in a path. It's an assembly without metadata. When we generate another net module, it's another assembly without metadata. And then we link them together. Those steps are done in parallel here, but they can be done in different ways. I can drop my net modules today and then come back and link them tomorrow for execution. And so what you get is another layer of abstraction, right? Unless you link those net modules together into metadata, it's not a DLL. Crazy. Another thing is that you can actually instrument your UXC that your executable.config to say, okay, well, I have a dependency on my code, my C# code or whatever. And here's where ironPython resides. It's on the network somewhere. As you execute, as you bootstrap, bring it in. Okay, that's the third way of doing it. And then you can get crazy with this, right? Like you can do reflection, calling C# from within Python, calling Python from within C#, creating engines, bunch of evasion going on here. You can achieve more stealth if you, for example, create different files and you load dynamically from one to another. But all in all, is the more reflection you can get, the better it is for you as an offender, and the worse it is for defense to actually flag. Okay, so recon executing, it's all good and well. Can we exploit things with this whole concept that we just talked about? Well, yeah. I mean, your code is data and your data is code, so your shell code is data that gets dropped into either REPL or extension, CSX extension, or you can actually compile it into a DLL, or you can compile it into module, and then you can call it, right? So the way you can do this, you can actually hide shellcode into a memory map file, and then you can point to that memory map file and execute that. So again, you have this division of responsibility. Your compilation, your code is not executable, you're just bringing it in as text, and then you create memory map files, for example, that live and act as storage for your shellcode that you're actually pointing to. Pretty powerful. You can add other things like you can bring code as a zip archive, and the story goes from there. Like however many layers you can add on top of it, that much the defenders have to work, right? And as we know, tools can only go maybe 1 or 2 steps beyond, and then the more things you can obfuscate, the better it is for you. And here's an example of, for example, you're creating your C# payload for Metasploit, right? And so it's a sliver code that you dump into shellcode into your C# or Seesaw in this case, and you dynamically execute this. Same way as you did C#, you can do a Python version of it, right? But in this case, look, we're actually not in a real Python, we're in Iron Python. We're actually bringing system threading from .NET. We're dropping the shellcode into a buffer, and then we're sending it off to Metasploit server, whatever the case may be. And then if you lack every single thing that you need and you actually want PowerShell, you can invoke it right from within your Seesaw or Delirium, right? You can actually invoke it from Python or C# by creating your regular process, and then you can, encode to your heart's content. That's also an evasion. So your PowerShell is not executed from command line, it's executed from a third party that may call another third party, and you get the idea. Okay, so development with Delirium, development with Iron Python is also really fast because what we're after is fast retooling, right? Like we need to be able to develop faster. So we have to have facilities in the language to be able to do what we did in PowerShell or what we want from C#. So you've got lists, you've got dictionaries, you've got the entire battery of things that come from Python right in here. So you can go pretty far with this. So Delirium also achieving its goal. It's leveraging DLR, avoiding PowerShell logging, while maintaining scriptability, interop, and drop down into direct.net. You do and achieve a bunch of stealth benefits by toggling Python from C#, C# from Python. And so, yeah, I mean, you can basically start coding in this. So this whole idea with Seesaw and Delirium is that managed execution toolkit, right? It's the execution, compilation, invocation of your code dynamically on your Windows box with the help of just .NET, with the help of interop from .NET into anything that you want, from loading your assemblies to loading your unmanaged COM+, ActiveX. It is also a fair number of stealth techniques that you can actually do to avoid defenses. And what do we learn from this? Well, application whitelisting is key. Every time you get any executable, it may be a slim cradle like we talked about, right? It's a cradle that is not fingerprintable, it's new, no one's using it. We're dynamically building our offensive tools on top of it by bringing payloads as code, right? And so even though the small cradle may not be malicious, it is a huge stepping stone for some things that you're doing on the box. So application whitelisting is key. Beyond that, if you are not able to do so, then for Seesaw part of it, you need to watch for csc.exe execution or artifacts, okay? Because they will code gets compiled and leaves artifacts. So you watch for those ephemeral artifacts in temp directories. You do not rely on DLLs being DLLs. You also need to to understand that they can be net modules, so you can actually somehow fingerprint them. DLLs for .NET don't have to be .dll, they can be .temp, right? So don't rely on your fingerprinting by names. Collect code and command lines from traces of csc.exe to see what actually is being compiled and what the attacker is trying to do. For Delirium, dynamic Python, it's harder. I will admit that you need to watch for loading of embedded DLLs as resources, which is a non-instrumented system. It's very, very hard to do. You need to, right now it's not hooked, but it may be in the future. Right now, somehow you need to watch for invocation of Microsoft.scripting and Microsoft.dynamic namespaces. Probably, even though it's used in a lot of places, it's a valid DLL. IronPython did DLL used for development everywhere. Somehow you need to put a marker on it and say, am I allowing this or not? Right? And so your mileage may vary. So this whole thing is that application whitelisting is key. Your slim cradles will become weaponized. They will get to the point where you can actually achieve a lot more strength, and you will just lose them in the ether, right? And so the code is there. This proof of concept code is there on the GitHub. Play with it, contribute to it. It's a work in progress. It really is just work in progress, but hopefully that gave you some ideas of how offense moves. If you're on the offensive side, then you may enhance or grab some ideas from it. If you're on the defensive side, also know that these things are happening and they're being used. Questions? No? Okay, thank you. Thank you all.